Good day and welcome back for the fourth part of our discussion on continuity. In this video, I want to focus in on a specific consequence of continuity, a property which is known as the intermediate value theorem. And to work us towards a statement of the intermediate value theorem, I want to first remind us of the intuitive concept of continuity. Intuitively, a function is continuous if we can sketch its graph without lifting up our writing utensil. And that intuition is really going to be enough for us to get the desired property today. So to begin, let me ask you to think about a question. If you have a function f, and you know specifically that the function output at a is smaller than some number n, which is smaller than the function output at b. And we're thinking, a to b is some interval where the function is defined. So graphically, I have n, which is some number between f of a and f of b. What I want to know is when you sketch the graph of the function f, does it have to cross this horizontal line? And I want you to pause the video and think about that for a few minutes and come up with your conclusion. And hopefully you've thought about this for a moment. And the answer is it might, but does it have to? And unless we add in some extra hypotheses, it does not have to cross that line. So let me draw kind of the generic example where it does. I start at a comma f of a, and I just draw the graph of some function connecting up to that point b comma f of b. And immediately we notice there's this point on the graph which corresponds to some input, let's call it c, where we have this point c comma n on our graph, that is to say f of c is equal to n. So in terms of the wording of our question, does there have to be a c in between a and b where f of c is equal to n? Well, there certainly can be, but could you draw another picture of the graph of a function where you do not have to cross that line? And this is the time to do that. Pause the video, take 30 seconds. And hopefully you've done so. Now if I start at this point a comma f of a, and maybe I just proceed along, but remember, I don't want to cross that line. So I'll just put an open circle here, and I'll just jump above, and then I will continue on going. Now, note, in this case, there is no input c where the output is n. That is to say, the function does not cross or touch that red dashed horizontal line. And note the reason we are able to do this is because we have what we might think of as this jump discontinuity, where the function is discontinuous because you're taking a jump. So in order to force such a c value to exist, what you need is a hypothesis that the function is actually continuous on that interval of interest. And this leads us into the intermediate value theorem, which whenever possible I will just abbreviate as IVT, and you are certainly more than welcome to do the same. So if f is a continuous function, and that hypothesis of continuity is extremely important, as we see above, on the closed interval from a to b, and n is a number between f of a and f of b, then the conclusion is there is a input value c in between a and b with f of c equals n. And one thing I want to note immediately before going any further, this is extremely important. Whenever we use the intermediate value theorem, we have to be very careful to verify and state that this continuity hypothesis is satisfied. And let me go ahead and write this down. So if we are ever going to use the intermediate value theorem, we must state / verify that the function is continuous. And usually it's as simple as just making a statement. So we just have to remember to do that, and in a moment we'll see precisely what I am talking about. For now, let me go ahead to make another observation of where this might come up. We can use the intermediate value theorem to determine if a function has a root in a given interval. And in order to maybe explain this, let's just note that the picture above, if you want to think about showing that there is a root, i.e. a spot where you cross the x-axis, this would occur if the n value happened to be 0. So we're just going to simply take this picture that we have above, and we're going to shift our graph so that the n value is 0. So a specific version of this intermediate value theorem. So if you know your function is, let's say, negative at a and positive at b. So the graph looks something like this. Well, that is going to allow n to be some value in between a negative and a positive. So it could be 0. So when we connect these 2 points with a continuous function, no matter how hard we try not to, at some point in between, there's going to be this value where you cross the x-axis, which indicates that you have a root. So let's go ahead and put this idea to use for us. A common example involves the following. Use the intermediate value theorem to show that the given function has a root in between 1 and 2. And just to make sure that we're all on the same page, when we say that something has a root, what we are really saying is there is a value c where the function output at c is going to be 0. And all we're going to do is try to just mimic what we see above, but since we're using the intermediate value theorem, we must state / verify that the function is continuous on some closed interval of interest. And let's just go ahead and note that the function we are dealing with is a polynomial. So since f is a polynomial, it is continuous everywhere. So specifically, it is continuous on the closed interval from 1 to 2. And that is precisely what I was referring to earlier when I said in order to use the intermediate value theorem, we must at least state or verify, if necessary, that the given function is continuous. Now, there's also kind of a secondary thing that we need. We need to note that there is some value between 1 and 2 where the function output is negative, and some other value where it's positive. Wherever those values happen to be is fine, because then somewhere in between there's going to be an input that makes the function 0 by the intermediate value theorem. And here it's as simple as evaluating the function at the endpoints of the interval. If you substitute in 1 for x, you get 4 minus 6 plus 3 minus 2, which is negative 1. If you substitute in 2 for x, you get 4 times 2 cubed, so 32, minus 6 times 2 squared, so 32 minus 24, putting us at a positive 8 currently, plus 3 times 2, so 8 plus 6, putting us at 14, minus 2 is 12. And to be honest, the number itself is somewhat irrelevant. It's just the fact that f of 2 is positive and f of 1 is negative. So now is time for the conclusion. So since f of 1 is less than 0, which is less than f of 2, by the intermediate value theorem, there is a c in between 1 and 2 with f of c equal to 0. And a few things I want to kind of highlight here. One of them is we know there is a c value where this occurs, but note the intermediate value theorem is what's known as an existence theorem. It tells us such a thing exists, but it does not tell us necessarily what it is or how to find it. Also, a common question that I would typically get at this point is, what if both f of 1 and f of 2 were positive? Well, then of course the answer is we'd have to choose maybe a different input. Then maybe we would try something like f of 3/2 or f of 1.75. So this one did work out rather conveniently. Also, the key ingredients that are absolutely necessary. So I need to see 3 things in an argument like this. The first is you're verifying the hypotheses of the intermediate value theorem. You're telling me that the function is a polynomial and hence it is continuous. And if it's not a polynomial, you're giving me the proper explanation as to what is going on. And secondly, you're finding those values, those inputs that make the function negative and respectively positive. And then lastly, the third key ingredient I need to see here is you're concluding. You're telling me kind of how the intermediate value theorem applies and then what the corresponding conclusion is. So that completes our discussion in this 4th part of continuity. And this is the part where if we were meeting in person, I would have another of these in-class worksheets for you. And there's only a few questions on the in-class worksheet, 3 of them. You can find it located in Canvas. And what I recommend doing is going to that in-class worksheet, pulling it up, working on it for 25 to 30 minutes. Give yourself plenty of time. Really focus in on trying to understand the key ideas and concepts. And then in our next video, I'll go over problem 2 on that in-class worksheet. And additionally, you can find full solutions on Canvas. Additionally, remember there are plenty of good suggested problems in the textbook, and truly focus on understanding the material. So stay tuned and take care.